Hello, and welcome to lesson 14 of this Introduction to Linear Algebra with Wolfram U. The topic of this lesson is applications of determinants. So let's begin with a brief overview of the lesson. So in the last lesson, we talked about the various properties of determinants. And now in this lesson, we'll switch over and talk about some applications of determinants to real problems. And the application will be things like linear systems, solving them, a formula for the inverse of a matrix, etc. So that's the theme for the lesson, applications of determinants. So let's begin with Cramer's rule, a classic application of linear algebra. So in 1750, Gabriel Cramer gave a method for solving the matrix equation Ax equal b using determinants. And the idea is this, that suppose you have an invertible n by n matrix, like this one over here. So the columns are A1, A2, up to AN. And let's say you want to solve the system. What you do is you first of all define the matrix AI of B by simply omitting the ith column and replacing it by the right-hand side B. And then Cramer's rule says that the solution vector X for the system has got components given by xi equal to determinant of ai of b or determinant of a. It's a very simple, elegant formula for solving systems. It works really well for small size like 2 by 2 or 3 by 3, and in fact, that's how you might learn this at school or college. Okay, so as an example, here is a 3 by 3 system, and you want to solve it using Cramer's rule. So first of all, we set up the matrix of coefficients. So you have 1, -2, 1, 0, 2, -8, and -4, 5, 9 from here. And the right-hand side vector is 0, 8, -9 from the right-hand side over here. You then form the determinants required for Cramer's rule. So let's say the first determinant over here is obtained by replacing the first column by the right-hand side, 0, 8, -9, etc. And then you can quickly work out the solutions, solution components over here. So you get x1, x2, x3, and you can check the solution using Wolfram language. So that's the Cramer's rule for systems. It's a very nice, elegant way of solving systems of equations. Now, what might happen is that occasionally you have a parameter in your system. So like over here, you have x and y, which are variables, and then s is a parameter. So it's an unknown quantity, but you can still apply Cramer's rule. So you can say form the matrix A and the vector B. So A has got S and 2 as the first row and 1 and S as the second row. Work out the required matrices over here, AI of B, and find a solution. Now the point is that because you have a parameter, the denominator might become 0 for certain values of S. And the solution is valid if and only if this determinant of A is not 0. So let's solve that over here. And you see over here that that's true if S is either negative square root of 2 or positive square root of 2. And as long as you stay away from those two values, everything works just fine. So as a second application of determinants, let's talk about finding the inverse of a matrix. Okay, now in an earlier lesson we talked about the notion of cofactor. So let's say you've got a square matrix over here. You want to work out the inverse of A. And what you do is you first of all delete the ith row and jth column to work out Aij like before. Find the cofactors, which are just these matrices over here, but with a factor of -1 or +1 as necessary. You then define the adjoint of A by taking the transpose of the cofactor matrix, and very soon you have a very nice formula for the inverse in terms of determinants. So that's one way of finding the inverse using determinants in this case. Okay, so as an example, here you have a 3 by 3 matrix. Let's check it's invertible. Well, determinant is not 0, so it's invertible. Work out the cofactors. There are 9 of them over here. work out the adjoint matrix, compute the inverse, and you can then check that the inverse is actually correct in this case. So the idea is to compute the cofactors over here in the normal way and then work out the inverse. But that's a very nice application of determinants. Next, let's talk about determinants and area. So let's say you have a parallelogram which is defined by the columns of a matrix A. So you think of each column as somehow giving you information about the parallelogram, then the area of this parallelogram is given by the absolute value of determinant of A, because you might have a plus or a minus sign over here. So let's say you have a parallelogram whose vertices are given over here. So A is the origin 0, 0, B is 3, 2, C is 8, 3, and D is 5, 1. Okay, now what you do is you first of all work out the matrix for this parallelogram. And that's just given by 5, 1 and 3, 2 as the columns. And you can work out the area quite quickly. So determinants really correspond to areas in this case. And similarly, you can talk about determinants and volumes. So let's say in 3D, you have a parallelepiped, right, which is determined by a matrix A. Then the volume of this parallelepiped is given by the absolute value of the determinant of A, just like in 2D. So for example, here you have a parallelepiped which is determined by A, B, C, and D. So you first of all write down the matrix, which is 1, 0, 2 from here, first column, 1, 2, 4 from there, 7, 1, negative 1 from there. Work out the volume with the determinant and check the answer with the built-in function volume, and you get back just the same answer. So determinants correspond to areas in 2D and volumes in 3D. That's a really nice interpretation of determinants. Okay, finally let's talk about determinants and linear transformation. So let's say you have a linear transformation T whose matrix is capital A. Now take a parallelogram in the plane and compute its image under T. Then it turns out that the area of the image is given by determinant of A with the right sign times area of P. And you have a similar formula for 3D space over here. Okay, so as an example of that, let's say you have a linear transformation given by a matrix A over here. Work out the image of P over here under the transformation. Compute determinants. And you can now check the relation between these three. So determinant of Q, the image, is determinant of A times determinant of P. Let's check that over here. So the main point is that in this case, you can think of the properties following from the determinants of matrix products. Okay, so we have spoken about lots of application determinants over here, and it's time to summarize. So basically, we have learned to apply determinants for solving various problems. So for example, we talked about Cramer's rule for solving linear systems. We talked about finding the inverse of a matrix. We spoke about areas and volumes. And we spoke about the images of sets under linear transformations. So that's the end of the topic of determinants. And in the next lesson, we'll talk about eigenvalues, eigenvectors. But before that, do revise determinants. They are quite useful and important. I'll stop over here. Thank you very much.